Thank you. Thank you. We'll move, since we are running short of time, we will move to the next most awaited session, actually. Professor S.S. Iyengar. Sir, over to you, sir. Actually, I just like to read out your brief profile here. Dr. S.S. Iyengar is the Distinguished University Professor and Founding Director of the Discovery Lab and Director of the U.S. Army-funded Center of Excellence in Digital Forensics at Florida International University, Miami, U.S. He is also the Distinguished Chair Professor at National Forensics University, Gandhinagar, India. He has been involved with the research and education in high-performance intelligence systems, data science and machine learning algorithms, sensor fusion, data mining, and intelligence systems. Since receiving his PhD degree in 1974 from USA, he has directed over 65 PhD students and national 100 master's students and many undergraduate students who are now faculties at major universities worldwide, or scientists or engineers at national labs around the world. He has published more than 900 research papers and co-authored and edited 32 books. His path-breaking discovery, known as the Brooks-Iyengar algorithm, was discovered in 1996, which is a milestone in his career. This discovery has led to the breakthrough in the use of sensors in various applications across the globe. By adopting this algorithm, it was possible to use network of sensors which would give out precious outputs, though few of the sensors received wrong inputs or faulty sensors. This algorithm is relevant even today and has received the prestigious Test of Time Award for its contributions over the decade by IEEE Congress in the year 2019. Dr. Iyengar has received IEEE Fellow Award, ACM Fellow, AAS Fellow, and Fellow of Artificial Intelligence, AAIA, Fellow National Academy of Inventors, Fellow of Institution of Engineers, India, among many awards he has received in his career. He has also received the IEEE Technical Achievement Award in the year 1998. Dr. Iyengar is awarded the Lifetime Achievement Award at the International Society of the Agile Manufacturing at IIT BHU in 2012. He has received the Lifetime Achievement Award from IEEE High Performance Computing in 2019. He was also a Fulbright Distinguished Scholar and has received several honorary PhDs from around the world. He has been awarded the Lifetime Achievement Award for his contribution to the field of digital forensics on November 8, 2022 during the 7th Interpol Digital Forensics Expert Group meeting at NFSU, Gujarat, India. Over to you, sir. And we are privileged and honored to listen to you, sir. Professor Iyengar, sir. We are also having the presentation ready with us and we can share.
Okay, can you all hear me now? I'm actually in Poland because, I'm receiving an honorary doctorate from one of the prestigious universities in Poland. And I want to thank Dr. Balaji and all the organizers for giving me an opportunity to say a few words on a very important topic called reliable sensor fusion. So let's go to the first slide. I think if we can help us to move to the first slide, that
yes,
would be nice.
And just a second, sir.
Yes.
We were able to hear you. Only
yes,
we are missing your picture, but
okay.
everything is
That's fine, I guess. Yeah, no problem. And okay, so, this is a work which we discovered in 1996 with my student, Richard Brooks, who is now presently a professor at Clemson University in the United States. The whole idea here is, evolution of yeah, thank you. Evolution of, okay, before that, I want to thank, various people and even Dr. Balaji and many people and Dr. Kasturi Rangan and Dr. Naveen Chowdhury and, Dr. Sudarshan and a whole list of people, who are sort of supported in research and my work in India as well as around the world. Thank you, and I appreciate. And there are many students, that the students are the backbone for any professor who's been successful. Okay, let's go to the next slide. So let's to give you, okay, so I'm a distinguished university professor at Florida International University, and I'm also a professor at various national labs. Go to the next slide. So, there is a very important thing that I've been listening to many of the talks this morning as I was here in Poland. So the very interesting thing is you have large amount of data. Let's talk about sensor data. And, sensor data is very important for various application. And the evolution of the sensing, perhaps we started sometime in 1992, jointly with many universities around the world and the national labs, Oak Ridge National Lab. So there is a lot of interesting things that been going on in the context of IoT related cyber crimes. That we are talking about investigation of connected devices, sensors, and other resources. So the motivation in any of these kind of analysis is how do you able to get a correct output from many of these sensor applications. That's the whole idea. So what we are really looking at it is, it has got a lot of nice, interesting, when there is a cyber attacks, cyber warfare, or, even if there is an opportunity in the context of, an attack on an airplane by a terrorist profile. So there are a lot of interesting things. So we have a lot of these devices. We very much rely on inputs. That's very important because these are non-homogeneous sensors. So how do you sort of take these things for any network forensic analysis, create an accurate representation of the environment and the function it is supposed to do? That's the whole idea. Examples like autonomous vehicles, like GPS sensors, radar, and many of these things. Go to the next slide, please. And so what we are trying to do is when there are multiple autonomous vehicles operate simultaneously, one of the things that we are interested in is to kind of develop a consensus between their estimates to prevent any collisions. Now, this in the context of detecting, what are the sensors, what is the output of these sensors, and then there are three important components that we are interested in any of the forensic application. One is the accuracy of these data. That is, accuracy is basically a local objective that must be met individually by each of the devices in the internet. Then the consensus, because remember, when we have an IoT with so many devices connected to it, and so when it is kind of, when we are collecting the data for any forensic application, what we are really looking at it is how accurate is the data. Now, we remember anytime when we talk about sensors, they are very imprecise. So the question is, even assuming there are 20% of the sensors are not accurate, how do I able to get this output and trying to make an analysis on the forensic application? So in this talk, we are trying to define what we call as what is the trade-off between the two objectives like accuracy and consensus. So it is not just by experimental work. We have found, provided a foundational science behind all of those things. There is a lot of network forensic application, and I saw some of it very good, but we are trying to provide a real nice theoretical foundation and then experimental comparison on this. So that's the whole idea of these objectives of these problems. Okay, so go to the next slide, please. So this is what I'm going to be talking. So let's take for Internet of Things. So we talked about, and we saw an application also. There are a lot of related cyber crimes always takes place in network forensics, and that includes investigation of connected devices, sensors, and other resources. Go to the next slide. So when we have this kind of a thing, everybody knows where it can go wrong. Any of the devices that we have go wrong in the context, the person may have hacked a part of the system. That means the 20% of my system is not working. So with the remaining 80% of the data that we are trying to generate, can I be able to make an estimate on the forensic analysis and how reliable estimate is? So this is an example of a traditional forensic problem that takes place for many of these applications. Go to the next slide. So Internet of Things is one classic example. And then now when we go and sort of focus on the IoT sensors, then you see that, on one hand, we have a lot of microcontrollers, and the other hand, the IoT hardware. And so there are lots of sensors that we use in many of these applications. And one of the primary things that we try to do is to acquire. But you never know. In many of these applications, there are a lot of sensors are not giving accurate results. So let's assume when there is a network analysis that has happened, maybe in the firewall or at the back portion of the network. So, and there are a lot of sensors which are being used to see what kind of data that we are talking. So the whole idea and the premise of this is assuming the sensors are generating data, and these sensors are not very accurate for a typical network forensic application, then how do you sort of come up with an estimation, or how do you do a diagnostic analysis on this? Go to the, so we are talking about both the software and the hardware errors. So go to the next slide. So the components of the IoT system, which I already have talked about it, there's a connectivity and the sensing devices, data processing, user interface. These are some components. So there is an attack on any of these devices. It can happen by a hacker. Now remember, we are talking about designing what we call as, algorithms which act like cyber warriors to minimize the cyber criminal. So in other words, we need to understand the mind of a hacker, what exactly he's trying to do, how is he trying to kind of put the whole system down. So in order to do that, we collect a lot of data in the analysis process. So the data that we generate, they're inaccurate 20% of the time. They are not accurate. So with the data that we estimate and collect, how do we make an estimation? So that's where the focus and the premises of the science behind it. So go to the next slide. So there are different types of IoT sensors. I don't want to go into that. There are, there are hundreds and millions of sensors if you talk about a big network application, or maybe talking about a data center. This morning I saw some slides. So the whole idea is the sensors are not giving correct data. But assuming that we have at least the sensors which are 80% accurate, how do we come up with a diagnostic tool and a technique where we are able to provide a basic analysis on the network hacking or something like that? Go to the next slide. So that's the whole idea of it. So how IoT works, I don't want to talk about that. Everybody knows. And, basically it has a lot of these things. So basically there are three important components. So when the IoT starts working, and let's assume there is a hacking and we are trying to come up with some related cyber crimes investigation on that, which includes basically an investigation on every component of the cyber, including the types of sensors. So we are focusing on one component with many multiple sensors and which are not accurate and they are not reliable. And then how do we do that? So that's the whole idea of this. Go to the next slide. Next slide, please. So the communication module and things like that are fairly simple. Everybody knows it. And there is a model that we have developed, which is called the Brooks-Iyengar algorithm. So what in essence, go to the next slide, what we are looking at it is when we generate these data, okay, how, for example, this data that whatever we are generating can also be implied to some of the kind of the future market that we can think about it in the context of embedded systems. And then, it may have an application in agriculture where the sensors have failed, or it may be, it is because of the hacking, or it may be an application in autonomous or wireless connection. So these are the importance of diagnostic tool that what we have discovered and we have done. And I will show you after I give you the basic foundation on this. Go to the next slide. So this is the basic. So what are the challenges now? One more time, the privacy is important in many of these, and the absence of governance and the technological standardization, which are not there, because we saw, even in the panel, there are lots of nice ideas. We are talking about it, but still most of the areas, they are yet fragmented. So managing and forecasting a rapid innovation in a challenging to government applications are very, very important. So that's the whole idea. So now the next few slides, I'm going to present the foundation for that. Go to the next slide. So the most important things what we are talking about, a recent paper that we published in a very prestigious journal called Information Theory Workshop. So this question of diagnostic tool and coming up with an optimal trade-off and sensor fusion is the most important aspect. This is what we discovered in 1996 which had a lot of applications. So let me present in few minutes. The theoretical ideas are there. And of course, if somebody wants it, these are my colleagues and students at our university. Go to the next slide. So let's go back and, so we talk about a sensor network. So sensor network now, it's a collection of an autonomous wireless sensors. They're all distributed in space. Let's say in the IoT context, the sensors are connected wireless to distributed agents. The agents estimate a target variable by fusing the sensor output. Now remember, this target variable is the one which we are trying to detect the forensic problem that has been hacked. So application includes autonomous driving, target localization, beam prediction, and so on and so forth. Go to the next slide. So what we are tracking is the fusion. So the distributed agents, they receive a set of sensor measurements, okay? Now, each one of these agents estimates a target variable called X. Now, the sensor measurement will be very noisy, okay? The noisy because of the hacking that has taken place in IoT devices, and these noisy sensors, so the resolution of measurement inaccuracy is that creep in. And then the faulty, so not only they are noisy and faulty, so if that is the case, we are not able to clearly diagnostic a sensor hacking that has taken place, a particular one or a part of it one in the IoT devices. So the sensor malfunctioning or malicious of adversarial inputs has caused that adversarial input is basically the hacking process. Go to the next slide. So that is the system model. So the system model, so what we are trying to do is to define the system objectives in terms of diagnostic tool, minimize the distance between the estimate and the target variable at each agent. There may be a lot more, agents that we have. Now, and then we have to develop a consensus of minimizing the distortion between pace of estimate at the target in distributed agents. Because you understand, if there are million sensors, and let's assume 20% of the sensors have been hacked, then essentially we have 80. So we have to define a basic process of how. So we use the Byzantine agreement problem of the solution for the accuracy and the consensus. Go to the next slide. So this is basically the system model. Now, what has been done before? Nothing has been done. This work, what we have done in 1996, I am pleased to say to all of our Indian audience, this is going to be nominated for a Turing Award. The Turing Award is like a Nobel Prize, of course. So the consensus that took place in 1982, it's a Leslie Lamport, who talked about synchronization, clock synchronization and distributed work. And then there are other people. So they came up with a Byzantine sensor general problem. Then there are other people who talked about, how do you sort of look at, a reliable decoding in the presence of adversarial senders. The adversarial senders is basically the attack that I am talking by the hacker. So Lou in 2005, he studied a scenario for every function or a sensor, a local estimation before transmitting signal to fusion center. So the only work that happened in 2005 before the work which we did is an accuracy consensus. So what we are talking is, this is the prime contribution is, in spite of the sensors being faulty in many of the IoT devices, we are able to give a reliable estimate and say, this is precisely the hacking has taken place, and this is the footprints of these hackers. Go to the next slide. So the very interesting thing is, Mozilla in 1990, what he did was, he came up with a standard fusion algorithms for fault tolerance. So what in essence we are talking about coming up with a very network diagnostic tool in spite of being faulty data that we have collected. So that's why it is called fault tolerant network diagnostic tool. So an accuracy, very high order. Then our 1996 Brooks-Iyengar algorithm is one of the most famous algorithms. Please take a look at it in the web page, Wikipedia. How many applications have been used this algorithm in terms of detecting the diagnostic problem of attacking a network. So there are a lot of nice interesting things we did. So we have been providing a very beautiful framework, a framework, analytical framework. That's why this work has attracted attention, in operating systems. See, this work has been used in the operating system because you remember in the operating systems Unix, let's assume you run a program and let's assume somebody attacked the operating system. So you are able to sort of isolate faults from all of these programs that you're compiling. So that has been used in Unix operating system. And then it has also been used in the regular automated metro trains in China, because you remember whenever there is an opening and closing of the door in many of these metro train, sometimes it doesn't get closed even when they started moving. So we have the sensor network, and let's assume it may have been also hacked because they have made it not to close. So we are able to estimate precisely how much of inaccurate data that we can have and still able to solve the problem. So that's the second application. There are applications that have been used in agriculture where assuming there are sensors that have been placed in the control room to a particular area where you can actually inject some enzymes into the plants and see how the growth of the plants can grow in very aggressive